but let me explain a little more, because last time I didn't have enough time to explain how to use the stack data structure to implement recursion. So I want to use another 10 minutes to complete this story. All right, so let's move. We are here. Oh, sorry, here. All right. Okay, all right, So here I want to use a simple example to give you the basic idea. It's very easy to understand. Let me use a specific recursive function. So the Fibonacci numbers. Let me use the famous. Later we will learn the Fibonacci numbers. But here, because that number is pretty simple, right? Fibonacci numbers. To calculate, there is a recursive formula. F of n equals f of n minus 1 plus f of n minus 2. That's the simple recursive formula. All right. Now, let's imagine. So we want to calculate certain Fibonacci number using the recursion. Here I draw a stack to implement that. Okay. So suppose this is an empty stack. So we want to use to calculate the Fibonacci number. Suppose our goal here, we want to calculate Fibonacci number f of 6. Relatively small. Because our stack is very small here, so I cannot do a large number here. We call f of 6 initial value here first. F of 0 equals 0. F of 1 equals 1. Okay? Initial values. All right. Now, we want to find f of 6, but f of 6 is not available. F of 6 equals, so here, f of 6 equals f of 5 plus f of 4. But f of 5 is unknown. F of 4 also unknown, right? That means f of 6, we do not know its value. Then you push into the stack. F of 6. Push into the stack. We delayed it. Push into the stack. That means we want to delay its calculation. Because at this point, we do not have enough information to calculate. So let's put it on hold. Okay? So that's the idea. Then that means we need to find a value f of 5, f of 6, f of 4. But f of 5, we do not have enough information for f of 5, so we push into the stack. F of 5. F of 4, we don't have information, we push into the stack. Okay? So we are here. Okay? All right. But when we get to f of 2 equals f of 1 plus f of 0. So here. F of 2. So there we have enough information. So f of 2, because we can use the initial value, f of 2, we can find a value. After we get f of 2, we can calculate f of 3, because f of 3 waiting inside the stack, because it equals f of 2 plus f of 1. F of 1 is known. F of 2 we just calculated, right? So then we can find f of 3 its value. After we get f of 3 value, then we can calculate f of 4 equals f of 3 plus f of 2. And so on. Then eventually you get to f of 6. Okay? You get to the bottom of the stack. Yeah. So when you use recursion, the internal implementation is like that. Okay? Yeah. Yeah. Like that. You stack data structure. Yeah. You hold, you store it. Okay? Yeah. But the reason I want to tell you this kind of internal implementation, then you will know how much memory space you need to use. You need to store this whole stack. If your stack is very deep, you need a lot of memory space. Okay? The stack could be very deep, right? Think about it. You want to calculate f of 10,000. How about that? F of 10,000. You push into the stack. Your stack could be very deep. Yeah. You heard of stack overflow, right? Yeah. So if the stack run out of your memory, then you get a stack overflow error. So then your whole program terminates immediately. Yeah. So that's a runtime error. Runtime error. Yeah. So that's the drawback, right? So you can see disadvantage. Yeah. So you need to use a lot of memory space. And you can encounter the stack overflow, runtime error. That's the cost. Yeah. So you need to pay that cost in order to use the powerful recursive algorithms. Yeah. Yeah. Later. Yeah. After we discuss the power of recursion, then later we can come back to consider how can we improve. No, because that step too deep. Can we shrink? Make the step not that deep. Yeah. Yeah. Use less memory resource. Yeah. Yeah. All right. Problem number 7. Calculate the factorial. Yeah. Yeah. Factorial, very easy to calculate, right? Yeah. So actually, this simple example, we do not need a recursive algorithm, right? Yeah. But here for education purpose. Yeah. So we intentionally use the recursive way to understand this factorial calculation. Yeah. Although we don't need, right? Unnecessary. Yeah. In the real world, nobody uses the recursion to calculate factorial, right? Yeah. Yeah. It's it's a bad way. Yeah. It's a bad way. But for the education purpose, yeah, it's a good example. Okay. Yeah. All right. So we want to use a new way to understand this factorial function. Method 1, iterative. Iterative, you just write a for loop to calculate factorial. Yeah. Very easy. Yeah. So we don't need a recursion. Yeah. Yeah. So by the definition of the factorial, you just write a simple for loop. Yeah. So here, everyone knows how to write it. Yeah. All right. But here there is an initial value. Do you know the 0 factorial equals 1, not a 0? Do you know that? 0 factorial equals 1, not a 0. Can you explain why 0 factorial is not a 0? It is 1. Can anyone explain a little bit? Yeah. It's not that simple. Yeah. Because usually people feel 0 something. Yeah, usually it's 0, right? Factorial. Because factorial, you use multiplication. When 0 involved and you do multiplication, how you get a non-zero number, right? Yeah. By intuition, it looks like we should get a 0 number, right? Yeah.
Does it have to do by representing, for example, 1 factorial as like, is it similar to explaining why something to the power of 0 is 1?
Yeah, power 0, 1,
Power of 0 is
0, 1, yeah, yes, a little, right. But this time, yeah, your power 0, the base is a non-zero number, right? Yeah, but here it's harder to understand because the 0 appear at the lower level, right? Yeah, not the exponent level. Yeah, yeah. So this we can use 2 ways to understand. Yeah, here I like to, we want to understand naturally. We should have some natural way to understand. Right? But there are 2 ways I can use to explain why 0 factorial must be 1. Yeah. If it's 0, then you get trouble. Okay, 1, so that everything, is compatible. Yeah, otherwise it's not compatible. Okay, all right. Yeah. Yeah. Implementation, 1 for loop. Yeah, we can skip. Yeah, because it's so easy, right? Method 2. This time, we want to use the recursion to understand factorial. Yeah. How to do it? Yeah. So, as a learning, because our first recursion example should be very simple, right? Yeah. Factorial is a simple example. Yeah. So let us use the recursive algorithm to implement n factorial. Yeah. The idea, so here we use a general problem solving approach. Yeah. In the problem solving, divide and conquer. You know divide and conquer, right? Yeah. So our module 4 will be, the title of our module 4, divide and conquer. But here we get that situation. So we want to do divide and conquer on this n factorial. Yeah. So let us write the formula. Yeah. Yeah. Because divide and conquer. Yeah. So when we divide a problem to be a smaller problem, the smaller the problem, the easier to solve, right? Yeah. So that kind of understanding. Yeah. Yeah. So when we work on a problem of the current size, assume that the problem of the smaller size has been solved. Yeah. So here. Yeah. Yeah. So these 2. Yeah. All right. So although I write these 2 steps here, but we need to use, after a few examples, we can understand these 2 statements better. Yeah. All right. Yeah. Yeah. So divide and conquer. So first we divide this problem to, smaller problem. We cut it somewhere. Yeah. Yeah. All right. So then this part is a smaller problem. Yeah. Smaller, then easier to solve. Easier to solve, but you can imagine we have solved it. Yeah. We have solved it. Yeah. All right. Then, if you go back to the original problem, there is a gap, right? Yeah, because the solution of the smaller problem and the solution of the original problem, there is a gap between them, right? So you need to fix that gap. Then you complete that recursive formula. So that idea. Yeah. All right. So let's do that. Yeah. Yeah. So this is the factorial formula. Let's divide it. Okay. Yeah. All right. Yeah. Before we do, let's introduce a new function called f function. F of n represent that factorial. Because when we do recursion, we need a function, right? Yeah. We need a name of that function. Yeah. Yeah. So f of n. Then we divide. Yeah. We cut off the last element. Yeah. So the size reduction by 1. Yeah. So you may ask why you just cut 1 element off, right? Not 2, not 3. Yeah. Yes. Yeah. 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 By experience. Okay. Yeah. Here, just every time we just reduce the problem size by 1. Yeah. one by one. Yeah. 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 Sometimes we need to reduce more. Yeah. Later we have a few other examples. You know, we need to reduce the size more than one. Yeah. But here, so one is a commonly used method. Yeah. All right. Then the remaining part, f of n minus 1. Yeah. Then you compare. What is the difference between f of n and f of n minus 1? There is a small gap, right? Yeah. Yeah. You need to fix that small difference, that gap part. Yeah. Yeah. So the gap part, the fixing formula is this. F of n equals f of n minus 1 times n. Yeah. Yeah. So you need to multiply the n number to connect the solutions of two adjacent problems. Are these two problems two adjacent problems? Right? Yeah. Yeah. F of some number, that's the current problem, right? Yeah. Here you have the solutions, the values. These two values we treat as the solutions of these two adjacent problems. Yeah. But these two adjacent problems should be connected in certain way. Which way they are connected? This way, okay? You just multiply that n to the solution of the smaller problem, then you get the solution of the larger problem. So that's your understanding, okay? All right, so this is the, recursive formula, all right? And it is correct, this formula is correct for n greater than 0, right? Yeah. Here, this n cannot be 0, right? Yeah. Yeah. So you need to specify the range for the n. Yeah. For n greater, strictly greater than 0. Yeah. Yeah. All right. Now we want to use this recursive formula to understand 0 factorial equals 1. Yeah. All right. To see that, yeah, can we write that recursive formula in this way? F of n minus 1 equals f of n over n. Yeah. Just algebraic operation, right? Simple algebraic operation. F of n over n equals f of n minus 1. Yeah. Equivalent representation. All right. Now, with this formula, can we plug in n equals 1? Yeah. Make n equals 1, both sides. Yeah. Then the left-hand side, f of 0. The right-hand side, f of 1 over 1. What is f of 1? 1 factorial. 1 factorial is 1. 1 over 1 is 1. Now, f of 0, that is 0 factorial, right? Based on our definition. Yeah. Now, if we let 0 factorial be 1, it is compatible with this formula, right? Otherwise, it won't be compatible. Okay? So if you make 0 factorial 0, then this formula won't be true, right? So it won't be compatible, not compatible. Okay? You get trouble. Yeah. Yeah. In math, so all our formulas must be compatible. Okay? Yeah. So you cannot get contradiction. Yeah. Yeah. You cannot get any contradiction in your math formulas. All right? Yeah. So that's the first explanation. Yeah. Second explanation. Yeah. Because we are computer science students, so we have a lot of programming experience. So here, I want to use our programming experience to explain. Yeah. Also makes sense. 0 factorial equals 1, not 0. All right. Here, in our computer science programming, we need to do summation, right? How do we do summation? Suppose you need to, given an array. Yeah. So let's assume. Oh, sorry. Yeah. This kind of thing. Escape. Oh, escape. Yeah. I need to, happens frequently. Yeah. All right. Given an array A from 0 through n or n minus 1, whatever. Yeah. So here for simplicity, let me just use n. Okay. If I ask you to do summation of all the elements in this array, so usually the usual method we use, we need to use sum variable, right? When we start, our sum variable equals 0, right? Because we want to accumulate all the values when we run the for loop, accumulate all the values in this array for, I from 0 through m, just sum equals sum of a of I, right? Is it summation, right? Yeah. All right. Then, next, I ask you to calculate the product of all the elements in the array. Okay? Product, yeah. Summation, product, it's different, right? Yeah. When you need to calculate product of the same array element, same array, but we do product, all the elements in the array. Do we need to create a product variable? What initial value you want to use? Product 1, right? Yeah, not 0, right?
0.
Yes. We need to, our initial value must be 1. Okay? So then we run the for loop from 0 to m. The product equals product multiply the a of I, right? Yeah. See? For product, the initial value must be 1. Okay? All right. Now, when we calculate factorial, it's a product. All products, right? Yeah. So you should use initial value 1. All right. Then you run for a loop. 0 factorial, that means your for loop is empty, right? Your for loop does not have any element, right? You don't need to do any product, right? Yeah. The initial value remains. Okay? Initial value is 1. 1 remains. So although officially you need to do consecutive products, but 0 number of products. What's the meaning of that? When you do consecutive product, you need to do 0 number of products. That means no product to do, right? But initial value is left. Right? So that's the second explanation. That's the reason 0 factorial equals 1. Okay? Yeah, these two ways to understand this formula. Yeah. All right. Yeah, so we complete this factorial problem. Yeah. All right. Yeah. Oh, question, Zane? Yes, don't worry. I will check your name after class. Okay? Yeah. Yeah. So that's our, first example, recursive algorithm example. Second, 8.2. Yeah. So this one. Yeah. Yeah, let me check how much time I have. Oh, a lot of time. Yeah. Because this example relatively long. Yeah. So I want to see if I can complete this example. Yeah. So I have enough time to complete this example today. Yeah. Power of recursive algorithms. Yeah, we want to see how powerful. Yeah. Because based on our initial analysis, the stack, very noisy. Yeah. Because we can, when we apply the recursive algorithm, there is a potential technical problem, right? So that, the stack could be very deep. Then we may have that stack overflow problem, right? Yeah, that's the runtime error. Okay, yeah. Stack overflow. Yeah. run out of memory. Yeah. Then, everything is gone, okay? All your calculation in your current program is gone, okay? It's not, other things, yeah. Yeah, so, all right. But why we still want to use the recursive algorithm? Because of power, yeah. Okay. So this problem, when we have more experience, we can try to find a way to, compress the stack. Okay? Compress, to avoid that stack overflow. Yeah. All right, let's look at problem number 8, Tower of Hanoi problem. Yeah. So, I think most of you should have the experience playing this puzzle, right? Tower of Hanoi problem, the puzzle. The interesting, non-trivial. So you need to make some effort, but not too hard, So usually for the puzzle, the most popular version is the 3-disc version. You have 3 pegs. You need to move the 3 discs in different sizes in a stack, following 3 rules. You have to follow these 3 rules. Otherwise, too easy, right? From one peg to another peg. Okay. All right. Let's look at these 3 rules. The first rule: only one disk can be moved at one time. So not the whole stack you carry, from one disk at a time. That's first rule. Very simple. Okay. Second rule: a disk cannot be placed on top of a smaller disk. Okay. That rule. Larger one you cannot put on top of smaller one. So always smaller one on top of larger one. The second rule. Third rule: all disks must be stored on a peg except while being moved. Move in the air, right? You move the stuff, going through the air. But you cannot put it on the table, right? So when you put it down, has to be on a peg, one of the 3 pegs. You cannot put other places. The third rule. So following these 3 rules to solve this puzzle, a little challenging. Okay? So you need to, find a well-organized way, right? You cannot just try random way, right? You have to use some well-organized way. So that's the challenge. All right. But here in this example, there are 3 disks. But our goal, we want to solve n-disk problem. N-disk, the general n-disk problem. They're much harder, right? So you think about how to solve this Tower of Hanoi problem with 100 disks. 100 disks. So very hard to imagine, right? But here, n could be any number. So at the end, we want to solve this problem. For any positive n number, we can find a solution. How hard? So that's why if we can solve by recursion, then it can show the power of recursion, how powerful it is, this method. All right, so let's do it. Analysis. How to solve the general problem with n disks. So in this module, we need to change our thinking habit. Because our usual thinking habit, we do the straightforward thinking, right? So one step by step, okay? Based on our logic. But this time, our thinking, we need to change the thinking way a little bit. The thinking way is, we need to split the problem into 2 parts, divide and conquer. That divide and conquer way, split the problem 2 parts. Then, the smaller part, we make assumption. If you do not have the training, you may not be used to, this way. If you're not in a good training, yeah. So because usually people do not assume a smaller problem, the solution is available, right? Because when we solve n-disk problem, we assume the n-1 disk problem has been available. We're making that assumption. But if you do not have a training, you do not like to make that kind of assumption, right? Yeah. For example, when I need to ask you to solve the Tower of Hanoi problem with 100 disks, yeah, 100 disks, yeah, then usually people say, oh, it's too hard. So how can I get it started? But it's rare people assume the problem of 99 disks has been solved, right? It's hard, right? Yeah. Because our current thinking, we assume the problem of Tower Hanoi problem with 99 disks has been available. We make that kind of brave assumption. But usually people won't make that kind of assumption, right? Yeah. But in this module 3, divide and conquer, recursive algorithms, we will make that kind of assumption. If you get used to this kind of thinking, recursive, then your problem solving skills will be much stronger. Okay? Much stronger. Yeah. So we need a practice. So we need a training. We need a practice, yeah, in this kind of thinking. Yeah. All right. So let's continue. When we start, we know it's a hard problem. When we have a hard problem, so far at this point, yeah, what do you want to do based on what we have learned at this point? Yeah, yeah. In this situation, we have this situation several times. What do you want to do? This problem is very hard. But how do you get started? Do we have similar experience before? Evan, similar experience before? A little bit? Yeah. Think about, we have a strategy before, I talk about before, when we have a hard problem, do we want to start from the small cases, simplest cases? Yeah. Look at it. What's the simplest case here? One disk trivial, right? Yeah, one disk trivial. Yeah, so if a trivial, we skip the next one. 2 disks, how about that? 2 disks, you need to do something, right? 1 disk, 1 move, you're done. Okay? Let's think about 2 disks. Can you solve 2 disk problem? 2 disk Tower Hanoi problem? Yeah, you have 3 pegs, right? Yeah, so 1 and 2. These 2 very easy. You don't worry. Then the next one is 3, P of 3. Yeah. The current puzzle, 3 disks. 3 disks. Yeah. So our first non-trivial. Yeah. Yeah. All right. Non-trivial. But when you solve a problem with 3 disks, can you assume solution for the problem with 2 disks available? Can you assume that? Because we did it, right? We did it. So then we do not have problem to assume that. Yeah. Yeah. When we work on the problem with 100, it's hard to assume the problem of 99 available, right? It's too hard to jump that big. Yeah. Here, it's not hard. Yeah. It's easy, yeah, because we just did it. Yeah. All right. So now you do not have a problem. We assume a smaller problem has been solved. Smaller problem has been solved. So we're very comfortable. Then, if you know a problem with smaller problem size, has a solution has been available, what do you do next? Our goal is we want to find a solution of the original problem. And we know a problem just one size smaller. The solution is available. So what do you plan to do to get the solution of the original problem? There is a gap, right? Yeah. These two solutions, there is a small gap. Yeah. Hopefully that gap is not very big, small gap. So you only need to work on that gap part. Then you're done. Yeah, so that's the analysis. Yeah, working on that gap part. Okay, all right. Yeah. Yeah. All right, so here, yeah, yeah. So our discussion. Yeah. So here we already use the recursive thinking. Yeah, because in order to solve problem of size 3, our starting point is problem of size 2. Yeah. Our starting point, much higher. Okay, not from 0, right? Not from nothing. Our starting point, because now we have a stepstone. Okay, the solution to that problem of size 2 is a stepstone. Okay, so we have a pretty good stepstone. Okay, we don't need to start from scratch, right? Yeah. Okay. Yeah. Can we use this stepstone, relatively high stepstone, to reach our current solution? Yeah. So, yeah, that's the question. Yeah. All right. Yeah, not trivial. Yeah, but yeah. All right. Now let's do the work. Yeah. Because we have that problem. Yeah. That's the beginning state. Yeah. The state at the very beginning. Yeah. All right. That the first move, you can only move the smallest disk, right? Based on the 3. Yeah. Remember those 3 rules. Yeah. We cannot violate any of the 3 rules. The first one, move the smallest disk to peg 3. Yeah. Then the second smallest disk, yeah. So we can move to the middle peg, right? Peg 2. Yeah. Yeah. Peg 2. Yeah. So what's the next move? Yeah. Can you tell me? What's the next move you want to do?
Smaller one to a little side one.
Good. Yes. Yeah. All right. So the next move. Yeah. Then we can move the largest disk to our destination peg. Yeah. Let's assume peg 3. That's our destination peg. Okay. Yeah. Yeah. But before we do that, can you see we just did P of 2? We saw, we apply P of 2 solution, right? Yeah. We just solved a Tower of Hanoi problem with 2 disks, right? Yeah. After these a few moves. Yeah. All right? Yeah. So after that, yeah, we move the bottom disk to the destination peg. Yeah. After that, can you see we just apply the solution of 2 disks solution another time to solve the whole problem? Yeah, because here you need to move these 2 disks on that destination peg. That's another solution, right? Another P of 2 solution. Yeah, yeah, another P of 2 solution. So then, smallest disk to peg 1, the middle disk to peg 3, the smallest disk to peg 3. There, we're done. Yeah. 7 moves. Yeah. 7 moves. Okay? 7 disk moves. So we complete this puzzle. Yeah. After that, yeah. So any conclusion? Yeah. After this experiment, remember our goal, we want to solve P of n. That is our goal. Okay? Yeah. Our goal is we need to find a solution of P of n. Yeah. But this experiment, we want to get some experience from this experiment. Yeah. And we want to generalize this whole process, yeah, to give us the solution for P of n. Yeah. Then 100, 200, even 1 million you can solve, right? Yeah. Or at least theoretically, 1 million you can solve. Although you do not have that resource to do 1 million disks. Yeah. But, theoretically, yeah, you can solve it. Yeah. All right? Yeah. Let's do the n disk. Let's solve the n disk problem. So next step, solve the n disk problem. This time, when we work on the general n disk problem, can we assume the n minus 1 disk problem has been available? Can we make that assumption? Do you feel okay to make that assumption? The solution of the n minus 1 disks available. Do you want to make that, aggressive assumption? Yeah. With this experience. Yeah. Because if P of 3, now you have no problem that P of 3 available, right? Yeah. Do you have a problem P of 4? Can be solved, right? P of 4 solution. You can make it, right? P of 4. After you make P of 4, can you make P of 5? After you make P of 4, can you make P of 5? Then, if we do this kind of things, then any number you can make it, right? Yeah. Any n number, you can find a solution. Yeah. So, yeah. Based on that understanding, so we can comfortably assume P of n minus 1 is available. By recursion. Yeah. Yeah. Why? Because P of 1, that's a recursive call, right? P of n minus 1. Yeah. By recursion. Eventually, P of 1 will be available, right? By recursion. Yeah. So, yeah. You can use the recursion to understand why P of n minus 1 is available. Yeah. By recursion. Okay? It is available. All right. Now, let's do it. N disk problem. Yeah. All right. Yeah. So that's the important step. Yeah. You assume that solution is available. Yeah. All right. So let me use the diagram. Yeah. Although here, because I cannot draw n disk, I still use the 3-disk version, but we treat that stack, that whole stack contains n disks. Yeah. Yeah. Let's imagine. Yeah. It's an n disk stack. Okay. All right. Then when we make a move, yeah, because our goal, we want to solve this P of m problem. N disk size problem to that destination. So this is the 2 peg, that's the destination from the source peg, okay? Temporary, intermediate, temporary peg. All right, yeah. Then, because we assume P of n minus 1 is available, yeah. Okay? By recursion, P of n minus 1, this solution available. Can we apply P of n minus 1 solution here? Yeah, we can. P of n minus 1, yeah. Yeah. We take the top n minus 1 disks, then we apply P of n minus 1, move this stack of disks to the temporary peg. We can do that, right? Yeah. By recursion, we can do that. All right, then the bottom disk, because the destination peg is empty, so we can move the bottom disk largest to the destination peg. Yeah. All right. Yeah. All right. Yeah. That's sorry. There. Yeah. So here. Yeah. All right. let me just draw. Yeah. All right. So move the largest disk, yeah, to that. Then after, can we apply P of m minus 1 the second time to move, the top n minus 1 disks to the destination peg? Yeah. Yeah. So here you can see we apply P of n minus 1 twice. In between, we move the bottom disk. In between, we need to move the bottom disk. That's the general solution. All right? Yeah, that's general. Then, the last step, we need to write a pseudocode. Okay? Yeah. To implement this idea. Yeah. All right. Move disks, the function. Yeah. The first parameter, that's the n number, right? Yeah. The number of n disks. Yeah. And you need to have 3 peg. So we use, 1, 2, 3. Okay? Yeah. Yeah. 1, this peg 3. Okay? 2, temporary. Okay? In this format. All right. Then, recursive function call, the first recursive function call, we need to apply that n-1 solution. Okay? So this function, n-1 solution. But the 3 pegs, the order of the 3 pegs should be different. Yeah. The source, 1, yeah. But the destination is, peg 2 is the destination. Okay? Peg 3 is used as the temporary peg. Yeah. All right. After that, then we move the bottom peg from the source to the destination. Okay? Source to the destination. All right. After that, then we do another n-1 version, the solution, and the 3 pegs, yeah. Source, peg 2 is the source. Okay? Peg 3, the destination. Still the same destination. And peg 1 is the intermediate peg. Intermediate. In that way, so you can see we complete the whole solution. Yeah. And by recursion, the whole algorithm is so simple. Yeah, just a few lines. Okay? These are a few lines. And any number n, you plug in, you can find a solution. Yeah. Then, think about how powerful this recursive algorithms, how powerful it is. Yeah. Can you imagine if we could not apply recursive algorithm? How hard to solve this problem? Yeah. Yeah. If you are not, think about, if you are not allowed to apply recursive algorithms on this puzzle problem, how hard it is. Yeah. Then you can appreciate the power of recursions. Power of recursion. Yeah. That's why even if the stack, that kind of resource problem, potential resource, we don't want to, give up this powerful method. Yeah. All right? Yeah. All right. Yeah. So that's the, how much I want to talk about for this part A. Yeah. Yeah. Then, yeah, because we have a lot of time, so I want to start part B. Yeah. Part B. So we can get started. Yeah. All right, so let me switch to part B. Yeah. All right. Part B, the topic, variable size reduction. Now it's another, every time we do one size reduction, reduce the size number by 1. Yeah, it's a commonly used method, but there are many other different ways. Yeah. So the title, variable size reduction. All right, yeah. So let's look at the question. Problem number 9. Count binary digits. Yeah. Although it's not very hard, yeah, but we use recursive algorithm. Yeah. Yeah. Later you may argue we do not need a recursive, just like factorial. We do not need a recursive algorithm. Yeah. Because count number of binary digits, if you can convert it to, think about it, convert it to the binary format, then you can count out binary digits easily, right? Yeah. So it's not hard. Yeah. But here we want to use the recursive way to solve this problem. Okay? All right. Yeah. Given a positive decimal integer n, then we need to do this. Find the number of binary digits in its binary representation. Yeah. So very simple, pretty simple. Yeah. But this time we use the recursive function to solve this problem. Yeah. All right. Review. Yeah. Let's review the binary representation. Yeah. In our discrete math, yeah, that course, discrete math. Yeah. So you learn the, binary representation, right? Yeah. How to represent a decimal number as a binary representation. Yeah. So we have that standard formula. Yeah. Standard formula. Yeah. Because when we represent a binary, we use the number base. 2 is the base. Yeah. Decimal, we use 10 as the base number, right? And here, the binary system, 2 is the base number. Yeah. Then, the bits, the coefficients for different terms, the bits, be 0 or 1. Yeah. Yeah. 0 or 1. Yeah. So less than the base number. Yeah. All right. But the most significant bit cannot be 0. Yeah. 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 The most significant bit cannot be 0. Okay? Yeah. So that requirement. So this is our standard binary representation. All right. Yeah. All right. Based on this representation, yeah, that b sub s must be 1. Yeah. If it's 0, then you just use the lower bit term. Yeah. You do not use this term. Yeah. So you can assume b sub s equals 1. Yeah. All right. Then, next, if we can represent in this way, then our answer is s plus 1, right? Okay. Because we count the number of coefficients, b0, b1 through bs, so total s plus 1. Yeah. But the question, we need to write s in terms of n, right? Yeah. So in our answer, we can only use the input number n. S is an intermediate variable, right? S is an intermediate variable. And you cannot use the intermediate variable in your final answer, right? Yeah. So you have to use the input information in your final answer. But the temporary intermediate data you cannot use in the final answer. Yeah. All right, so how to find S, the question. If we can find S in terms of n, then you get a final solution. That question. Yeah. All right. Look at that formula. Can you use divide and conquer way to derive a formula for that S? Yeah. Divide and conquer. Yeah. 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 So that divide step is important. Yeah. This place, the divide step is important. Yeah. So when you do a special operation, here, yeah, you want to reduce the problem size, right? Yeah. So you want to reduce the problem size. Yeah. Yeah. When you reduce the problem size, what are the usual ways we do to reduce the problem size? To reduce let's say reduce the number, yeah? Because the problem size here, n is the problem size. Yeah. N is the problem size. Okay? To reduce the problem size n, yeah, from this formula, yeah, what are the usual methods we can use to reduce the problem size n? Yes, yeah, that kind of operation. Yeah. So usually, when we say reduce value of some number, usually we use two commonly used methods. One is subtraction, another is division. Okay? Subtraction, you make it smaller, right? Division, you can also make it smaller. Yeah. But when you look at the formula, the structure of that formula, which way you want to do it? Subtraction or division? Preserving the structure. Yeah. When you do that operation, you don't want to mess up, that structure. The structure is important. You want to preserve that nice structure. This is the structure, okay? Yeah. This binary, that's the nice structure. So you don't want to break it. Okay? So you want to preserve it when you do the operation. All right? Yeah. Division by 2, how about that? Division by 2, both sides. Integer division. Integer division by 2. The right-hand side, when you do division by 2, you get the same structure, right? Yeah? Integer, b0 over 2, because integer, if it's less than integer, the fraction part, we drop it, right? Yeah. When we do integer division, the fraction part, we just throw away. Yeah. All right. So then we do integer division, division by 2, both sides. All right. Here. All right. Division. Left-hand side, n over 2, but we take floor function, right? Take floor function. Yeah. We know it's integer division. Yeah. Integer division. But here, mathematically, in order to avoid confusion, we use that floor function. Okay. All right. So right-hand side, b0 term is gone. Yeah. Because b0 over 2, less than 1, so we drop it. The b0 is gone. Okay. Then the remaining terms, there. The power of 2, the exponent number is reduced by 1. Division by 2, cancellation, right? Power of 2, reduced by 1. All right. Right. From this formula, can you see some size reduction? Yeah. Because now the problem size becomes approximately half of the size, right? That's the size reduction. Okay. So we do size reduction. Okay. Yeah. Then our intermediate conclusion, not the final conclusion. Okay. Yeah. We need to make a conclusion, but it's an intermediate conclusion. Our intermediate conclusion, when we represent this n over 2 floor function number in the binary representation, how many bits do we need to use? S, right? Yeah, because here, after we drop that n0, so we only have S, right? Yeah. Before we drop n0, we have S plus 1. But after we drop n0, b0 is gone. b0 is gone. So we have S bits left. Yeah. So here you can see at the left-hand side, when we reduce the problem size by approximately half, the right-hand side, the number is reduced by just 1. Okay? Yeah. All right. Now, we need to, based on these two formulas, the observation on these two formulas, now we can derive the recursive formula. Recursive formula. Okay, all right. Yeah. All right. Yeah. Yeah. That's our observation, right? Yeah, by half. Yeah, so after these observations, then our recursive formula becomes, because we need to introduce function. Yeah. Okay? Yeah. The function. Binary recursion, this function of n, size n, equals this function, but on a smaller problem size, the difference, the gap part, the gap difference is 1. So you add that difference 1 back to the solution of the smaller problem size, then you get a solution of the original problem size. That is the recursive formula. How we derive recursive formula. Okay? Yeah. We compare solutions of 2 problem sizes. Then we look at the difference, the gap part, the difference. Then, we get equality. Yeah. Yeah. All right. Next, we need to solve this equation, right? Yeah. So recursive. This equation, we need to find a solution. Although you can write a program, yeah, after you derive this recursive formula, you can run a loop. Yeah. Not necessary for loop. You can run a loop to calculate, or recursive call, to find the final solution. Yeah. But here we want to find a math formula for this function. Math formula. Because this equation is not very hard. So we can find a math formula. Yeah. But we need an initial value. Yeah. 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 The number of bits for 1, okay? 1, yeah, is 1. Yeah. Binary represents also 1. Yeah. So 1 bit. Yeah. All right. Yeah. All right. Next. So now we need to find a solution. Yeah, let me see how much time I have. Yeah, just a few minutes. Yeah, just a few minutes. Yeah. All right. Next. Yeah, so this is our, the problem we want to solve. Yeah. All right. Yeah. And here, that division by 2, actually in computer science, we know division by 2, that's just a left shift operation. When you implement division by 2, internally, there is a very fast operation. Yeah. Because in general, so if it's not division by power of 2, if it's a general division, the operation is very slow. Operation is very slow. Yeah. Addition, multiplication, division. Here, let me give you some information. Inside the computer, in CPU, the number of time used. All right. Yeah. So let me addition. So we use addition. The CPU time used for addition. Yeah. So we use, let's say, 1 time unit. Okay. 1 time unit as 1 unit. Usually in several nanoseconds. This unit is, 2 or 3 nanoseconds. Okay, yeah. Approximately 2 nanoseconds. Okay, all right. That's addition. Then multiplication. Multiplication, 10 units. 10 units. Okay. That's slow. So that's why in our polynomial evaluation, we use 1 to 10 ratio, right? Yeah, so based on this. Yeah. Then division, okay? Yeah. But division is not power of 2. Power 2, you do shifts, then faster than addition, okay? Shift operation, even faster than this addition. Okay? All right. That fast. Because you just move, shift. That's faster than addition. Okay? division, (40 units). That's slow, 40 units. Division. Much slower than multiplication. Because division, that's slow. All right. But here, fortunately, we only need to do shift operation. We do not need to do non-shift division. Okay, in the hard way, shift. That's why people like the shift operation. So fast. Okay, all right. Then, all right. So here, then, for the basic operation here, this addition, we treat as a basic operation. Then we define a function a of m as the number of additions, because we want to count the number of basic operations. So here, so we use this a function, although a function closely related to the that b something function. Okay, but here we use to count the number of additions, and we have the recursive formula. The recursive relation similar to that version, but the meaning is slightly different. The meaning, so we count number of additions. Okay, all right, This one, because this one, we just imagine 0 plus 1. Although it's unnecessary, right? But here, in order to match the original, so we just make it a 1. Then, let us solve. Actually, the same version. Just the meaning slightly different. All right. How to solve it? Let me leave next time. Okay? Because it's a long story to solve. All right. So let us leave it next time.